Okay, good morning to all of you. I'm audible. Fatima. Okay. So, dear student, is there any doubt regarding the last lectures? Okay, now, so as we have started the convection. So, my dear student, as we know, just consider a flow of fluid or flat plate. Just continue from that. Just consider a flow of fluid or flat plate. This is what the flat plate. This is what the leading edge of the plate. It's X, and this is what the Y. And I told you to the fluid flowing past the flat plate because convection heat transfer takes place between the flowing fluid and the surface. So the fluid flowing with the velocity of u infinity and temperature is T infinity. So as you know, if any fluid flows, there is always formation of velocity boundary layer. Why? Because as the fluid come on the contact with the surface, the velocity becomes zero, no slip condition, and as the fluid move away from the surface, the velocity of the fluid get increases, and that causes the boundary layer formation. So what I drawn here, this is what the velocity boundary layer, and the thickness in the y direction up to which the gradient exists, that is called as boundary layer thickness. So this is what the boundary layer thickness is a boundary layer, and this is called as boundary layer thickness delta h delta. Any problem, beta? This is u is a function of y. This we have already discussed in the fluid mechanics, where the velocity approaches nearly up infinity, u infinity. Now, similarly, if the fluid temperature and surface temperature are different, the velocity boundary layer will form always because always the plate is at the stationary. If the stationary plate is there and fluid come in the contact with the surface, no slip condition, there is a disturbance in the momentum, and that momentum disturbance is propagated in the rest of the fluid by the property called as anyone. The momentum disturbance which has been taken place on the surface of solid means only the first layer uh, is in that contact, but rest of the fluid is not in that contact, but still they are going to be affected by which property? Momentum diffusivity, not viscosity, Mr. Astos. It should be momentum diffusivity. Viscosity and density boss will play important role because I told you density will important for the inertia and the viscosity is important for the viscous force. है ना? Yes, kinematic viscosity or momentum diffusivity. Can you should say kinematic viscosity or you should say momentum diffusivity. At the same time, if I am talking about the thermal boundary layer will form addition when the temperature of surface and temperature of flowing fluid is differ. Let's say surface temperature is maintained at the Ts. It's maintained. Anyhow, we maintain the surface temperature of the plate at Ts. Then what happens? There is a formation of thermal boundary layer. Okay, so at y equal to 0, temperature Ts. And if the surface and the flow temperature differ, there will be a region of the flow through which temperature varies from Ts at y equal to 0 to T infinity in the outer flow. That region is called as thermal boundary layer region. The region in which temperature variation is there, that region is called as thermal boundary layer. I told you already in the last in the fluid mechanics, the region in which the velocity varies up to thickness up the region up to which the velocity varies, that is called as velocity boundary layer region. And similarly, the region up to which temperature varies, that is called as thermal boundary layer region. And thermal boundary layer region may be smaller, may be larger, or may be same size of velocity boundary layer. That will depend upon different case that I will discuss later on. Clear, beta? So if at the same axis, if I am going to draw here, so at surface y equal to 0, surface temperature is Ts, and as we move away from the surface, temperature get decreases like this. And this layer may be more, just I am going to draw with this. The red is TBL and this is VBL. Now, thickness of thermal boundary layer may be equal to the velocity boundary layer, may be more than velocity boundary layer, maybe equal to boundary layer, anything is possible. That depend upon the property called as thermal diffusivity. Because just I told you here thermal disturbance takes place on the wall, on the surface of the plate, yes or no? Just like momentum disturbance has been taken place, similarly here thermal disturbance has been taken place. And the thermal disturbance which has been taken place on the wall, because only the fluid layer which on the surface, you can say the immediate layer on the of the fluid layer on the surface will be at temperature Ts. I'm talking about the immediate, the red line. This is the first layer of the fluid which is just on the surface, that will be equilibrium with the surface temperature. But any layer above that, that is not in direct contact, but that's why its temperature is different from the Ts, and that temperature difference causes temperature gradient, and this temperature gradient causes the heat transfer. Clear beta? So just like here the thermal disturbance has been taking place on the wall, but that thermal disturbance is propagated in the rest of the fluid, will get propagated in the rest of the fluid by a property called as, by a property that is called as, anyone? Thermal diffusivity. Analogous term is there, thermal diffusivity. Whatever momentum disturbance, because all the layer of the fluid is not in direct contact with the surface, but still they are going to affect it. So it's just because of a property name is called as thermal diffusivity. Clear beta? Thermal diffusivity. So the thermal disturbance which has been taken place on the surface of the plate, that get propagated in the rest of the fluid, that by the property of the fluid, that is called as thermal diffusivity. Okay? So depending upon the two diffusivity will takes place, means the momentum disturbance propagated by the property of fluid is called as momentum diffusivity. And there is alpha is called as thermal diffusivity. ठीक है बेटा? तो the thermal diffusivity act as a messenger for propagation of heat diffusion, and this momentum diffusivity act as a messenger for momentum diffusion. So when the fluid flowing over the surface of solid and its temperature is different from the temperature of surface, that causes the heat transfer, and there is a formation of thermal boundary layer just because of variation in temperature, and that heat transfer get propagated in the rest of the fluid by a property is called as thermal diffusivity. So whatever the heat disturbance has been taking place, that propagated in the rest of the fluid by a messenger called as thermal diffusivity. It means through the wall that momentum and heat both get diffuses simultaneously. There is simultaneous diffusion of, just like there is simultaneous formation of velocity boundary layer and thermal boundary layer, similarly there is simultaneous diffusion of momentum and thermal. So depending upon which is dominating over the, now there is a name is called as Prandtl number. I will discuss later on Prandtl number. Prandtl number is nothing, it's simply a measure of relative importance of momentum diffusivity over thermal diffusivity. Clear? Momentum diffusivity over thermal diffusivity, nu by alpha. It's a ratio of momentum diffusivity or thermal diffusivity. Now tell me please, if momentum diffusivity will dominate over the thermal diffusivity, or if momentum diffusivity is faster than the thermal diffusivity, then what happens? Which boundary layer thickness is more? If momentum diffusivity is faster than thermal diffusivity, then thickness or variation in the velocity is more farther distance in the y direction as compared to temperature variation. That is different thing, more than 1, less than 1. Yes, in terms of thickness of boundary layer, if the momentum diffusivity is faster than thermal, means momentum diffuses faster than the thermal, than the heat, then obviously the variation of velocity in y direction is found to be more than temperature variation. then thickness of velocity boundary layer is more than, if I'm saying this as a delta th, and delta th is thermal. So can you say this Prandtl number, which is nu upon alpha, that can be approximated as, I'm not saying equal, but I can say more the momentum diffusivity, more the thickness of velocity boundary layer, है ना, and more the thermal diffusivity, more the thermal boundary layer thickness. So delta upon delta Ts means Prandtl number can be related with the thickness of boundary layer, thickness of velocity boundary layer to the thickness of thermal boundary layer, but they are not equal exactly. Equal is this, these two are equal, but this corresponds to this corresponds to this. Am I right? Bolo. So what is exact relationship is there? That is what Prandtl number equal to delta upon delta Th ke power 1 by 3. That I will show you in the later subsequent lecture. Have you ever studied this terms? 1 by 3. So when Prandtl number is more than 1, my dear student, when the Prandtl number is more than 1, then the thickness of velocity boundary layer is more than the thermal boundary layer. Okay, and when Prandtl number is less than 1, then the thermal boundary layer, it less than 1 means momentum diffuses faster, sorry, heat diffuses faster, then obviously thermal boundary layer thickness is more than the velocity boundary layer. And if Prandtl number equal to 1, then both the thickness are same. Clear? So which thickness is more, that is going to decide by the two term momentum diffusivity and thermal diffusivity. Clear? The convection heat transfer mode is sustained both by, I told you convection heat transfer is sustained both by random molecular motion and by the bulk motion of the fluid within the boundary layer. Yes or no? And why it is convection? Because the fluid is flowing and there is a random motion, as well as random motion means what? Diffusion as well as collision. So it is sustained by, or you can say convection heat transfer mode or convection heat transfer mode is sustained both by random motion, that is called as diffusion and collision, and along with random motion diffusion also bulk motion of the fluid within the boundary layer. And the contribution due to random motion, dominates at which location? At the wall or at far from the wall? Tell me please. Or near the surface? Near the surface. I told you the convection heat transfer mode sustained by both random motion as well as the bulk motion. So at the surface, which contribution is dominate? So conduction means what? Conduction means what? Conduction in the fluid means, what do you know by conduction in the what do you mean by conduction surface? Only random motion, because I told you conduction mechanism of conduction near the wall, mechanism of conduction in the fluid is random motion of the molecules only. Yeah, clear beta? And in fact, at the interface between the surface and the fluid, interface means here at y equal to 0. Interface कहाँ है? Where the fluid come into contact with the surface of solid, that is interface. So at the interface between the surface and the fluid velocity is 0, and the heat transfer mechanism is only by conduction, and that is random motion of molecules. And the contribution due to bulk motion originates from the fact that boundary layer grows. Now listen, how the bulk motion contribution will come into picture. The contribution due to bulk motion originates from the fact that, boundary layer grows as the flow progresses in x direction. That boundary layer will grows. That why it grows? Why it grows? Because I told you the velocity gradient is going to be decreases. And in order to compensate that reduction in the mass flow rate, because as I told you, why boundary layer thickness will grows continuously along in the downstream of the plate? I told you. Tell me please. Why do the boundary layer thickness grows in downstream of the plate? Because I told you now, as the fluid is allowed to be in contact with the surface of solid, more and more contact, more and more reduction in the velocity is there, and that reduction in the velocity causes the reduction in gradient. Huh? And due to this, the fluid will take longer distance to reach the 99% of overshooting velocity, because of velocity gradient decreases. Yes, velocity decreases as the fluid, not momentum diffusivity. यार कहाँ that so sad. Momentum diffusivity will play important role when the fluid gets changed, sir. Momentum diffusivity is what? Property of the fluid. And with the same properties there, then how can you say कि momentum diffusivity will change? I'm talking about same fluid is there, but if the same fluid is moving from 1 point to 2 point, sir, you should revise the notes, please. I told you when the fluid moves from 1 to 2, what happens at the same distance in the y, the velocity get decreases. Why? Because as the fluid cover larger distance, or fluid moves over the plate, the velocity get decreases. It's obvious. Then that causes this is u axis, this is y axis, that causes the reduction in the velocity gradient. It means at the same point, at the same location, here velocity is 1 meter, here it's 0.5 meter per second. So in order to attain the 99% of velocity or upstream velocity, the fluid has to be cover more distance in the y direction. That's why thickness is increases. So what I'm saying to you, the contribution due to bulk flow motion originates from the fact that boundary layer grows as the flow progresses in x direction, and that's why, since it grows, then whatever conduction heat transfer, whatever the heat transfer through conduction is taking place, the heat that is conducted into this layer, I'm talking about the layer above the surface. So heat that is conducted into this layer is swept downstream, is swept away, because fluid in the motion. That's why I told you na कि fluid is moving here. Then whatever heat has been conducted, that is swept away in downstream. Heat conducted in this direction, but due to motion, the heat gets swept away in downstream. Yes or no? That's why for the conduction, always the gradient is maintained here. Always the new fluid is maintained here. So I'm just talking about contribution due to bulk motion. How the contribution of bulk motion will come into picture. So I told you, as the boundary layer grows, as the flow progresses in x direction, the heat that is conducted into this layer is swept downstream, and finally what happens, that is transferred to the fluid outside the boundary layer. Because as the boundary layer grows, this will transfer to the outside boundary layer. As you know, already we have solved one question, there is some also mass transfer in this direction. Whatever mass has been transferred here, mass transfer through this layer, m1 is equal to m2 plus m3. Yes or no? That I have already shown you in the previous lectures. In the fluid mechanics problem, one problem we have solved. Whatever mass that has been entered through this, some of flowing through this and some of going out through this region, outside the boundary layer. So since mass is going to out, that's why along with the mass also energy will get out. So whatever the heat get conducted into this layer, that will swept away in the downstream, and finally what happened? Transferred to the fluid outside the boundary layer. Finally, that heat is transferred to the fluid outside the boundary layer. Clear? So that's why bulk motion has come into picture. Yes or no? What is bulk motion? Just like aggregates. So there is also contribution of bulk motion is there, but at the surface, near the surface, the heat transfer is only by conduction. But heat transfer through conduction, that will enter into the above layer, that will get swept away in the downstream, and finally get transferred to the bulk outside the boundary layer. Clear, beta? That's why bulk motion has come into picture. Clear? So what should write some point here? Already I told you these things, but still you can write one point that is important for the convection heat transfer is sustained by both random molecular motion, and second, bulk motion of the fluid. And I already defined the bulk motion of the fluid motion. Bulk motion of the contribution due to random motion is dominate near the wall, and contribution due to bulk motion will come into picture when we are in the away from the surface. Clear? And now convection heat transfer may classified according to nature of the flow. That's all about convection. Any problem? Now listen. So at the wall, you can write this, draw this picture at the wall. I'm going to draw again. I'm going to only draw temperature profile. Just draw temperature. You should not draw any arrow because temperature is scalar function. T is a function of y. This is what Ts. This is what the y. This is what the T is a function of y. because ये जो x एक्सिस यहाँ पे टेम्परेचर है, ये y एक्सिस है, ठीक है बेटा. तो यू कैन सी एज y increases temperature get decreases. This lines indicates the magnitude of temperature, and this is what the gradient. This is what the gradient, and that is what dt upon dy or dy upon dt first. Okay बेटा, this is what the gradient now, slope of this line, that's a gradient. So at wall at y equal to 0, at y equal to 0 plus means near the surface, it means near the surface. You can also write at y equal to 0 in general. Near the surface, heat transfer through conduction is taking place. Heat transfer through conduction, q conduction is there, q dot conduction, small q means flux. Conduction is equal to minus k, k of what, solid or fluid? Conduction is taking place in the fluid or solid? In fluid only, because solid is already asthermal. Whatever thickness is there, the solid is asthermal, my dear student. Temperature is constant, no heat transfer is there in the solid. Yes, that's why we should write the thermal conductivity of the fluid only. Is this clear? Minus k of f, that's very important. To avoid the to create a confusion, they also give you the k of solid, but there is no role of k of solid, only k of fluid is there. So minus kf into dt upon dy at y equal to 0. Clear? 0 plus or 0, whatever you can say. This is what the heat transfer by conduction. It's a heat flux by Fourier's law, and the same rate the heat conducted from the surface of solid in the rest of the fluid is going to be transferred via combined mechanism. Which combined mechanism? Random motion as well as bulk motion, and that's combinedly called as convection heat transfer. Yes, so that's why I should write here h into Ts minus T infinity. So why not I have written A? That's because of I write flux, and this is what the convective heat transfer is given by Newton's cooling law. Before this, you should write one point: the rate of heat transfer by the convection is given by, although now before this, please write. I just miss one point. The rate of heat transfer by convection is given by HA into Ts minus T infinity. Why Ts? Surface temperature. T infinity is the bulk fluid temperature. Okay. Now, and if heat transfer from T infinity, here this is the case if Ts is more than T infinity. If Ts is more than T infinity, and if T infinity is more than Ts, then reverse is the driving force. Clear? This is what the Newton's cooling law. It's called as Newton's cooling law. So what is Ts? Ts is the, and this Newton's cooling law is used to define the rate of heat transfer by convection, and where Ts is the surface temperature, T infinity is the surrounding fluid temperature, A is the heat transfer area, okay, and H is what? Heat transfer coefficient. It's very important term, heat transfer coefficient. Heat transfer coefficient. Heat transfer coefficient. Clear? Now listen, as I told you, convective heat transfer is strongly influenced by the flow field. Yes or no? Boundary layer phenomena is essential to understand the convection heat transfer, and boundary layer will always develop whenever the fluid is going to flow over this. So that's why I told you fluid mechanics will play a very important role in the analysis of convection, because convective heat transfer is strongly. Why strongly? Because as you know, when I increase the velocity, when on the same plate, let's say this plate is hot and this is at 100 degrees Celsius and the fluid flowing is at 20 degrees Celsius and the velocity was 1 meter per second. When I increase the velocity, resting as it is, what happened? The rate of heat transfer will get increases. Yes or no? For example, if you have hot boiled egg, if you are blowing air over through mouth and if you keep blowing air through blower or through fan, in the both cases rate of heat transfer is different. So what actually has been different? Is egg has been changed? No. Is temperature of the egg has been changed? No. If temperature of the air has been changed? No. What has been changed? the velocity of air. Is this clear? So this H, actually convection heat transfer is very complex phenomena. Why complex phenomena? Because the rate of heat transfer through convection is strongly influenced by the velocity of flow field. Similarly, if I just, let's say here, if I just keep the hot boiled egg into liquids, let's say here it's water and now here it's oil. Now both initially were at the same temperature of 100 degrees Celsius, 100 degrees Celsius, and the temperature of oil is 20 and water is also 20. Means surrounding fluid and surface temperature both are same, and both fluid are stationary. Both fluid are stationary. Although that causes the buoyancy effect, that is different thing. Huh? But initial final temperature of the Ts and T infinity is same. But now here it's water and here it's oil. Still the rate of heat transfer is different. It's the cooling time will be same or different. If I place the hot boiled egg once in the water and once in the oil, rate of heat transfer or time required for cooling the time required to cool the hot boiled egg is same or different. It is different. Why it is different? What has been changed? What has been changed? Is the velocity of the flow has been changed? No, both are stationary. Is the temperature has been changed? No. Its egg has been changed? No. So actually what has been changed? The fluid has been changed. Now it means the rate of convective heat transfer also depend upon the property of the fluid. Yes or no? The rate of heat transfer not only thermal conductivity but also on the density, also on the viscosity. So that is called as thermophysical properties. So my dear student, here you have seen the rate of heat transfer does not only influence by the flow velocity but also depend upon the property of the fluid. Flow property, fluid property. So along with the velocity, also it depends upon the thermophysical properties of the fluid. Why do we keep the bottles standing vertical in the freeze? What will happen if we keep the bottle horizontal in the freeze? In general, we used to keep the bottle, water-filled bottle in the fridge to make it cooled. Why do we keep the bottle only vertical? Why do we not keep the bottle horizontal? And what will happen if we keep the horizontal? Yes, it means it's also depend upon the how object is oriented for the flow, towards the flow. So, for example, let's say if air is flowing in this side, and if we keep the, let's say if I have a rod, hot rod, and if you want to cool this rod, one I place in this way and one I place in this way, then in the both cases the rate of heat transfer is different. It also depends upon the orientation of the object, and that's called as characteristic length. So at the last, my dear student, what do you know? Okay, this H is very complex because this H depends upon number of parameters. Yes, very good, Deepika. This H depend upon the number of parameters. H is a function of what? First, velocity, then thermophysical properties of the fluid, and also characteristic length of the object. Characteristic length of object. I am talking about this when there is no phase change. Only I am talking about the convective heat transfer that does not involve any phase change. Two types of convection problem is there. One is involving phase change and without phase change. So when I am talking about heat transfer, convective heat transfer that does not involve phase change, without phase change, then in that case the heat transfer coefficient depend upon the velocity of the fluid, thermophysical property, and also on the characteristic length of the object. So in short, you can say this H depend upon function of velocity, U, rho, mu, Cp, K. They are thermophysical properties: density, viscosity, specific heat capacity, thermal conductivity, and along with this LC. So 1, 2, 3, 4, 5, 6 parameters there on which this heat transfer coefficient depends. For which fluid? For convective heat transfer problem. For convection problem that does not involve phase change. When phase change is involving, like boiling and condensation, then along with the 6 more 2 parameter will come into picture, that is surface tension and also latent heat. along with the velocity, density, mu, Cp, K, Lc, that also depend upon the lambda, latent heat evaporation, and also on surface tension, because size of the bubbles will also depend upon the surface tension. So some more parameter will come into picture and complexity is going to be more increased. Yes or no? And already in the fluid mechanics we have seen, when any one dependent variable depends on more than one independent variable, then it is very difficult to show the effect of these parameters on the heat transfer coefficients individually. Because if you want to carry out individual experiment, then what should I do? I should keep the all parameter constant and change the velocity, and then we should show how the heat transfer coefficient will change. I told you in the last lecture in the fluid mechanics. Similarly, if you want to change the effect, if you want to check the effect of density on the heat transfer coefficient, then what should I do? I should fix the all parameters except for density, and vary the density, and you should say how the heat transfer coefficient is going to be with the density. Same thing with the viscosity, same with the Cp, same with the K, same with the Lc. Yes or no? So that is very complex. So instead of avoiding the complexity, what should I do? That complexity I can reduce by grouping the variables into the dimensionless groups or non-dimensionless numbers. Yes or no? That's why, my dear student, whenever I'm talking about the convection heat transfer, then dimensionless number come into picture. So dimensionless number come into picture just because of, you should say, because heat transfer coefficients is a very complex parameter. It's not a property. Listen, very important thing. Heat transfer coefficient itself not a property, but it depends upon the property of the fluid. And in order to know, because since heat transfer coefficient depends upon the various parameters, that's why in order to simplify the analysis, there is a method called as dimensional analysis method. Through this method, I can reduce the number of variables by grouping the variables into the dimensionless groups or dimensionless numbers. So that's why if you, then two number will come into picture for this case when that does not involve the phase change. Nusselt number is found to be function of Reynolds number and Prandtl number, and the functionality relationship, functional dependency of Nusselt number. This Nusselt number is, what is significance of Nusselt number I will discuss later on. This is H Lc upon K of fluid. This is Reynolds number. That is rho V bar or U infinity, whatever you can say, rho U infinity into Lc upon mu. Prandtl number is nothing, it's, I told you, momentum diffusivity upon thermal diffusivity, and momentum diffusivity is nothing, it's mu by rho, and alpha is what, K by rho Cp, I told you later on, and that's why rho cancel. This is mu Cp upon K, K of fluid. So these three numbers come into picture for which case? For convection problems that does not involve any phase. And the functional relationship between the Nusselt number, Reynolds number, and Prandtl. Now it's very easy to understand because now only three variables are there. As compared to previous, there was 7 variables. 1, 2, 3, 4, 5, 6, 7 variables are there. And to establish the functional relationship between 7 variables is very difficult task. And that's why there is a method called as dimensional analysis method. We had reduced the number of variables into only 3 numbers: Nusselt number, Reynolds number, and Prandtl number. Okay. And the functional relationship between the Nusselt number, Reynolds number, and Prandtl number can be found by the experiment, and that found in form of Nusselt number as a C into Re ki power m into Prandtl number power n, where C, m, and n are constants. That constants we can found from these constants C, m, and n. These constants are found from experiments. Yeah, clear beta? That's why this is called as empirical relationship. That's why it's called as empirical equation. Why empirical equation? The equation that we got from the experiment, that is called as empirical equations. Even though, listen, what the meaning is that although the convection is very complex phenomenon because it is strongly influenced by the flow velocity and flow property and types of fluid flow. When the flow is laminar, then the value of heat transfer coefficient is different. When the flow is turbulent, then the heat transfer coefficient is different. When the fluid is oil, when the fluid is water, means when the property of the fluid is getting changed, still the heat transfer coefficient is getting changed. And how the velocity I will discuss in the next lectures when I will start convection in detail. That's not in detail, it's only introduction part. When I will discuss, then I will show you at that time how the velocity affect the temperature, how the velocity gradient affect the temperature gradient. Although I am going to discuss by physically. Why physically? Because as the velocity increases, then whatever heat transfer via conduction through the wall, that is going to swept away the heat transfer, heat conducted or heat that has been conducted in this layer is going to swept away by the flowing fluid. That's why all time the new fluid is there. That's why the rate of heat transfer can be increased. Is this clear? It means if we increase the velocity gradient, so I will show you the velocity gradient will also increase the temperature gradient. Velocity gradient also increases the temperature gradient, my dear student. Okay, but for this system, is this clear? Convection heat transfer is sustained by the both random motion, random molecular motion as well as bulk motion. Bulk motion contribution will come into picture. I told you when the bulk motion is actually heat transfer through purely advection, and when the advection is taking place in presence of temperature difference or temperature gradient, that is called as. So I told you convection and advection. आइए 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 बाहर है, आइए आइए पहले बाहर आइए, बुला रहे हैं. Convection and advection. Convection term customarily defined for. Good morning. पहले गुड मॉर्निंग बोलिए पापा को. गुड मॉर्निंग बोल दिए. हाँ कस के बोलिए. गुड मॉर्निंग. पापा पैर छू लीजिए जल्दी से. तो हाँ आयुष्मान बाबा जाइए. हम मम्मा बाहर है, जाइए. माय डियर स्टूडेंट, कन्वेक्शन टर्म. The term convection is customarily used when referring to cumulative transport. Cumulative transport means random motion as well as bulk motion. The term convection is for cumulative transport, combined transport, random plus bulk, while advection is only for pure bulk. Clear beta? And when the temperature gradient is taking place with the bulk flow, that heat transfer due to pure bulk flow is called as advective heat transfer. And advective heat transfer plus convective heat transfer combinedly is called as convective heat transfer. Yes or no? That's already I told you. This is all about your. Now come to the types of convection. Now, convection heat transfer may be classified according to the nature of the flow. Yes or no? That's forced convection and free convection or natural convection. What is forced convection? When the flow is caused by external means such as by fans or pumps or atmospheric winds. For example, just you can use a fan to provide the forced convection, air cooling of hot electrical components or hot electrical object or hot object. If you want to cool the hot object and you place the hot object near the fan, that is forced convection. In contrast, what about the free or natural convection? The flow is induced by buoyancy forces, and buoyancy force is due to difference in density, and that difference in density caused by difference in natural or free convection. Yeah, very good. Free or natural convection. In the free or natural convection, the flow is not induced by external agency. Here flow is induced by buoyancy force. Flow is induced by buoyancy force which are due to density difference caused by difference in temperature. कोई problem better now? So write down please the types of convection. A convection heat transfer may classify according to the nature of the flow. According to the nature of the flow. Convection second is free or natural. निधि थोड़ा कूलर इधर कर दो यार, और दरवाजा खोल दो, थोड़ा सा हवा हवा आए, ये भी खोल दो. फोर्स और फ्री, ठीक है. व्हाट इज फोर्स कन्वेक्शन? Force convection when the flow is caused by external means. Yes, or agencies such as fan, pump, atmospheric air, atmospheric air or winds, atmospheric winds, blower, etc. ठीक है, तो that is by external means. Now when flow is caused by which flow? Bulk flow, caused by or induced by buoyancy forces. By buoyancy force, which are due to density difference, caused by temperature variation, in the fluid. ठीक है बेटा, so due to temperature variation, when the flow is caused by that temperature variation causes density difference, and that density difference is responsible for the buoyancy force. So when the flow is by buoyancy force, that is causes natural convection. Example is, for example, just you can consider a very simple example of pure force convection. Let's say this is what the electrical circuit. It is circuit board, and it is a hot element of circuit board. Have you ever seen the circuit board? Obviously you have seen. It's a hot components of circuit. On every circuit you might have seen like this circuit is there. In amplifier, they are hot component of the circuit boards. Hot components are there on the printed circuit board. So if I just place the hot air through fan, a large fan is flowing over it. It's force flow. Its air is flowing, and as the air is flowing, then whatever the heat transfer through this is only by Q by force convection. Yes or no? The cooling of this hot object is taking place by force convection because air is flowing over it. It is force convection. Now what is free convection? When this is vertical like this. Why vertical? Just I am going to clear, and you should answer yourself. Here air is not flowing actually, my dear student. Air is just moving without any force flow, because as you know, as the air will, because they are hot components, they are the hot components of the circuit, and they get heated due to electrical mechanism. Current is flowing and then they get heated. Then what happens, as the air as air surround that circuit will get heated, and when they get heated, then density become lower, they become lighter, and lighter fluid will goes up. Yes or no? And that causes a buoyancy effect. Lighter will go and heavier will come down, lighter will go, heavier will come down, lighter will go, heavier will come down, and in this way the heat transfer will takes place. That heat transfer is taking place again, that is by free convection. So this flow is basically because of buoyancy driven flow. So air that makes contact, any air that makes contact with the components experience an increase in temperature, and that increase in temperature causes the reduction in density, and since it is now lighter than the surrounding air, then buoyancy force is induced. Yes or no? Buoyancy force will induce, because lighter density and heavier density, there are two density difference. That difference in density will induce a buoyancy force, and buoyancy force induces a vertical motion for the which warm air ascending from the boards is replaced by an inflow of cooler ambient air. Yes or no? Already the cold air will come from the bottom and hot air will goes up. This type of flow is induced across the circuit. Yes or no? They are the colder air are heavier, and the air which makes that contact with the hot components of the circuit that get heated, temperature get rise, and rise in temperature causes lower lighter in density, decrease in density, and that density difference causes the, because ambient air is of heavier density, while the air near the surface of components, they are of higher temperature, that's why lower density. That density difference causes a force is induced, that is buoyancy force, and that causes the natural driven flow. This is pure convection, free convection. Yes or no? Bolo. And what happen if I make it horizontal? Why it's vertical? Because when, what happen if if just let, for example, if the same circuit is horizontal, then what happen? Obviously in that case the more circulation of the flow is there. Circulation is much more better in the vertical as compared to horizontal. Also there is there, because whenever any air is surround the direct contact with the surface, that will get heated, will become lighter, become glow up, and heavier density fluid or colder fluid will come down. That causes the current, but that current is more stronger in that vertical. Why, my dear student? Because along with the density there is also a natural flow is there because of pressure difference. Pressure here, the fluid having pressure is here P, and here the pressure is P naught is there, and P naught plus rho g h. H is the hydrostatic head. Yes no? Here is pressure is P, and here P naught rho g h. So this hydrostatic pressure difference also causes the driving force for the fluid to flow. Yes or no? So mainly we have to increase the circulation, but that circulation of the air is not because of force or any external agencies. That is naturally happen. Clear beta? Now this is what the pure force convection, this is pure free convection, but there should be also combined. When the combined is there, when the, because already I am not saying ki here the, obviously any air that get contact with the surface also get heated, and that become lighter will go up, and the lighter fluid or low temperature fluid which is heavier fluid will come down, but the motion induced by this is very less as compared to motion by the forced. Yes or no? Means mixed force convection, or you can say if the velocity is associated with the flow, if the velocity associated with the flow are small, or you can say buoyancy forces are larger, means the flow due to buoyancy is comparable to the imposed force flow, then we can say that a mixed flow is there. When the both flow, because two flow is going to induce here actually. One is flow due to natural convection and flow due to forced convection. So when the flow due to forced convection is comparable with the flow with the natural convection, then there is a mixed convection is there. Clear beta? Now if I just how it is possible to have a mixed convection in this case? When I use to fan here, this fan will blow the air. When this in between the circuits, if I place the fan, then what happen? That will obviously restrict the flow due to natural convection. When I use to flow, then that flow will assist the buoyancy force. When they will assess the buoyancy force, then obviously what happen? They just opposing the buoyancy flow. So that's what mixed convection is there. Or if you place the fan here, that fan will flow the air from here, and the buoyancy force will flow from opposite side. Then obviously that will restrict the motion of the buoyancy force. So this is mixed convection is there. So that's already you got to understand clearance about this. Any problem? So now depending upon, this is the one classification of convection heat transfer depending upon the types of fluid flow. Types of flow, based on the nature of the flow, the two convection is there, force and free. Now depending upon the phases involved, the two types of convection problem is there. One is convection that involve without phase change and with phase change. So without phase change means whatever example we have shown that does not involve phase change. For example, that I told you, the cooling of hot plate, flowing of air over the hot plate, cooling of hot boiled egg, or you can say cooling of this electrical circuit, or heating of any object. That is there any cases that I had discussed here that involve any phase change? No. But there is some example of convection problem that involve phase change, just like boiling and condensation. Clear beta? So in all example that we discussed so far of the convection problem, that only involves sensible energy is getting transferred. In all cases, the sensible energy or internal thermal energy of the fluid is getting transferred. The energy that is being transferred is the sensible heat or internal thermal energy of the fluid. Sensible, in form of sensible heat, the energy is getting transferred. Yes or no? But there are some problems associated with the convection problem that involve the phase change. For example, boiling and condensation. Clear beta? So that you should also write. I told you When I consider the convection problem that involving phase change, then it is much more complex because the two additional parameter will come into picture. One is the size, and size of the bubble is decided by surface tension, that you know, and lambda is the latent heat of condensation of evaporation of the phase change. So this is what more complex. Clear? This is all about your convection. Is this clear about the convection, my dear student? So ultimately the convection problem is very complex, but still the rate of heat transfer by convection is very simply given by the Newton's cooling law, that is H. So all the problem, all the complexity is associated in only calculation of what? H now? Yes or no? Because area is given to you, surface temperature is known to you, surrounding fluid temperature is known to you. All the problem is associated with only finding out the value of H. And is H is a property of fluid? Tell me please, is H is a property? No, it's not a property. But all the complexities of the convection heat transfer involves in H, because this H depends upon the number of parameters. Yes, it depends on the properties, it depends upon the viscosities, it depends upon the density, it depends upon thermal conductivity, specific heat capacity, characteristic length, and also velocity of the fluid. So if anyhow, it means all the complexity is in calculation of H. If anyhow you got the value of H for given condition, for given heat transfer problems, then I think its most easiest problem is convection heat transfer, because only we should put the value of H, because only all the problems is in the finding out the value of H for the given heat transfer problem. Yes or no? Because value of heat transfer coefficient is going to vary if we increase the velocity, if we change the density, if we change the shape and orientation and all. So if anyhow you got the value of H for the given prescribed heat transfer problem, then the very simple problem is the convection heat transfer. Just put the value of H and the A and all the parameters, then you can solve. Sir, I told you, Mr. Kedar, convection is not a heat transfer. Convection word is not only with the heat transfer. I told you what is meaning of convection. Deepika, please tell me, what do you know by convection and advection? Is the convection word and advection word is only with the heat transfer? I told you, Mr. Kedar, if you watch the lectures, if you read the lecture, if you read your notes, you found convection. The term convection refers to combined flow. It is only associated with the flow. Whenever I am talking about the convection, that is involve the cumulative term, and cumulative flow involved means whenever the flow is because of random motion as well as the bulk motion, that's called as convection. While advection only consider the pure bulk motion, and when in that types of motion, if the temperature difference or temperature gradient is involved, then that is called as convection heat transfer and additive heat transfer. Similarly, if concentration difference get involved, it's also possible, just like a temperature difference is involved in the in types of flow. If there is a concentration difference get involved, then also it is possible. Now, for example, in the mass transfer you will study, sir, if the fluid is going to flow, then obviously, let's say if the fluid is flowing past the surface of solid, and this, for example, this is the naphthalene plate, or let's say this surface of the plate is covered with the organic paints, organic volatile paint, and if air is flowing over it, what happen? When you put the paint over the surface, then obviously you might found ki the molecules of the paint get diffuses in the air. That's why we are able to smell. Yes or no? How do we smell the paint? It's just because of when the paint is going to be laid over, or when the paint is going to apply over the surface. Let's say a table is there, you want to paint the surface, you want to paint the surface of the table. And if once you painted the surface, मम्मा पूजा कर रही है ना बेटा, पूजा कर रही है ना, आप तो गुड बॉय है ना, जाइए आप भी पढ़िए, पापा पढ़ाई कर रहे हैं, आप भी पढ़िए, अपना बुक लाइए, अपना टेबल चेयर लाइए, जाइए. So whatever, when the air is flowing over it, then paint molecules are volatile in the nature, that will get diffuses into the air, है ना. तो any surface of air on the surface solid, they are uh, uh, nearly of low velocities or nearly stagnant. The velocity of air near the surface is stagnant, yes or no? So there is a also formation of, it's here the concentration is CAS and here Ca infinite. Ca infinite is the concentration of the diffusing species in the air, है ना. So as we move away from surface, there is a velocity boundary layer, there is also concentration boundary layer, because any fluid layer on the surface will be have Cas, and as we moving upward, concentration get decreases. This C is a function of y. So here CAS and here concentration get decreases, yes or no. So but whatever the mass transfer on the surface, that is only by the molecular diffusion, but in the rest of the fluid there is a motion is there. So whatever the mass transfer has been taken by the molecular diffusion, है ना, molecular diffusion, that gets swept away by the fluid flowing over it, and ultimately that will get out from the boundary layer. So that causes the convection, bulk flow will come into picture, yes or no. So mass transfer or diffusion that is happen by the molecular diffusion, random molecular motion only on the surface, that is going to be assisted by, or that can be further in the further layer of the fluid is going to be taken by the combined mode. Listen, I told you, just like convection word is not only for the heat transfer, it's also equally important for the mass transfer, because convection involves the combined mode of flow. Convection is actually the fluid types of fluid flow. The convective flow means that involves the random motion as well as the bulk motion. So similarly, when the mass transfer is taking place from the surface of solid, so near the surface the mass transfer is by purely random motion of the molecules, means molecular diffusion, and that mass transfer that has been happened by the molecular diffusion will get swept away by the fluid molecules, because upper layer in the rest of the layer the fluid is the motion, and that causes the bulk motion as well. So combined mode will come into picture here. So at a steady state, the rate at which, is this clear, yes or no, Mr. Kedar? Just like there is always analogy is there. Similarly, in the mass transfer, I will discuss the concentration boundary layer. Okay, sir. So here I am only going to concern about the heat transfer. Now, when these things all about, now come to the point here. As I told you, कि when the fluid flows over this, there is, this is what the temperature, this is T as a function of y, this is what the y, and there is a temperature profile, this is what delta Th, thermal boundary layer thickness, and this T is a function of y is shown here. Here temperature is Ts, here is T infinity, this I told you already. Now my decision, now come to this picture here. At near the surface, the heat transfer is by conduction, Q conduction, yes or no? And in the rest of the fluid, that random motion means in the rest of the fluid, at the wall, at y equal to 0, at y equal to 0 plus the Q conduction, which is equal to minus of Kf into dt upon dy at y equal to 0. This is the temperature gradient at y equal to 0. This should be equal to what? In the rest of the fluid, it is by convection, H into Ts minus T infinity. Yes or no? Tell me please. The Q conduction equal to Q convection. But this is the conduction at the wall, Q conduction at the wall, and this is the convection in the rest of the fluid. Listen, this is the series. Otherwise, always connect to heat transfer is more than the connect to heat transfer. But what I'm saying to you, whatever the heat transfer, whatever heat transfer is propagated through the wall by conduction, the same is going to be at a steady state. Let's say 200 watt is the rate of heat transfer by conduction. The same 200 watt is going to transfer in the rest of the fluid by convection. Yes or no? Same 200 watt in the rest of the fluid is going to be transferred by convection to combined mode. Whatever the 200 watt is going to be transferred near the wall by only random motion of the molecules by conduction, the same 200 watt is going to propagate in the rest of the fluid by combined mode. Because in the upper layer of fluid, there is fluid in the motion. Is this clear? But what the motion does? Now listen, when the velocity get increases, now your question should be, sir, then how the increase in the velocity will increase the rate of heat transfer? That is the question that you have in your mind, yes or no? I am going to discuss here. When you increase the velocity of the fluid, what happens? When you increase the velocity, then obviously velocity of each layer of fluid get increases. Let's say, for example, let's say this is what the layer, it's a plate is there, and try to understand carefully. This is what the first layer of the fluid. This is what second layer. Let's say first layer is very close and that is stagnant. Let's say the first layer I am going to show you on the surface only. And this is second layer. First layer, second layer. Its velocity is 0. And this is the profile, yes or no? And here 0 velocity, here 0, because this axis is velocity axis, u is a function of y. Here is 1 meter per second, let's say 1 meter per second. Clear beta? Is this visible to you? Okay, when we increase the upstream, let's say here velocity where u infinity where 5 meter per second. When I increase the velocity upstream from when the 5 meter is there, then at this distance of 1 millimeter from the plate, the velocity is found to be 1 meter per second. So what is the gradient? What is du upon dy? At wall, at y equal to 0, gradient means this is what a gradient is there. Change in the velocity is from 1 minus 0 upon 1 millimeter. Yes or no? So this is what 1 meter per second per millimeter. This is the gradient, yes or no? When I increase the upstream velocity from u infinity from 5 to 7 meter per second, then obviously every velocity will get increases. To add the second layer, that was velocity of 1 meter per second. Now it's become increased, yes or no? Bolo. So when the velocity get increases like this is become now, let's say 1.5 meter per second. Then what about the gradient here? What about du upon dy at y equal to 0? Now change the velocity is 1.5 minus 0 upon 1 millimeter, and this is 1.5 meter per second per millimeter. This is our gradient. So by increasing the velocity, what has been taken away? Gradient has been increased. And I told you, if you recall the lectures of fluid mechanics, by increasing the velocity gradient get increases, and ultimately we are increasing the Reynolds number. When I increase the velocity, then the Reynolds number increases, and as the Reynolds number increases, then thickness of boundary decreases. Why? Because now, since velocity get increases, now it will take a smaller thickness to reach the 99% of upstream velocity. है कि नहीं? Because when we are going to increase the velocity or increase the Reynolds number, what increases? The gradient get increases, and if the gradient get increases, then to increase now to attain the upstream velocity, it will require some somewhat shorter distance. Yes or no? Okay, now, so what happened? You have seen. Now, what about temperature gradient? So, as velocity, I will show you later on. Ki as the velocity gradient get increases, that will also increase the temperature gradient. That will also increase the temperature gradient. That I will show you in the upcoming lectures. But here, always the increase in the velocity. That's why whenever you increase the velocity, the heat transfer, mass transfer get increases. So increase in the velocity, du upon dy at y equal to 0 get increases. That also increase the temperature gradient, dt upon dy at y equal to 0, and also increases the dca upon dy at y equal to 0. Means that will increase velocity gradient at the wall get increases. That will also increase the temperature gradient and also increase the concentration gradient at the wall. And that increase in the temperature gradient increase the conduction heat transfer to the wall. Are you getting a point? Increasing the velocity gradient at the wall, that also increases temperature gradient, and as the temperature gradient get increases, then also increases the heat transfer via conduction through the wall. Now more faster the rate of heat transfer via conduction will taking place to the wall. Yes or no? So ultimately, by increasing the velocity, what does get increase? क्लियर है? बोलो. So indirectly we have increased the, when we increase the velocity of the fluid or velocity gradient at the wall of flow velocity, that will increase the temperature gradient as well as concentration gradient, and that's why their rate of heat transfer and rate of mass transfer through the wall get increases. Clear beta? So this equation is very important, my dear student. In this case, at the wall, minus k of f into dt upon dy at y equal to 0 is equal to h into ts minus t infinity. Then how can I find the h? Is minus kf into dt upon dy at y equal to 0 upon ts minus t infinity. Yes or no? And this is called as heat transfer coefficient. And you know, since temperature gradient at the wall, is it same at all location on the plate? If this the plate is there, is it same here, here, here and here? Just like simply, just you can, analogy is friction coefficient. I told you in the fluid mechanics. Friction coefficient is defined as tau w, and this is nothing, h is equal to, my dear student, it's qw, heat transfer through wall, heat flux to the wall upon ts minus t infinity. It's analogous to friction coefficient, that was tau w, wall shear stress. This is wall momentum flux and this is wall heat flux, and this was half rho u infinity square, and here it's temperature difference. Clear? Its analogy is there. It's friction coefficient, that is heat transfer coefficient, and since tau w is nothing, it's mu into du upon dy at y equal to 0. and since velocity gradient at the wall is going to change from one location to other location, yes or no, velocity gradient at this point, and the velocity gradient is maximum at the leading edge and getting decreases. That's why friction coefficient get decreases, and infinite at the leading edge. Yes or no? Same thing here. dt upon dy at y equal to 0 is maximum at the leading edge, and that get decreases along with the length of the plate. Clear, beta? And that's why this is called local heat transfer coefficient, Hx. Why it's Hx? Because Qw is a function of x, wall heat flux is a function of x, Ts minus T infinity. कुछ याद आ रहा है similarity? And Qw is nothing, it's wall heat flux, and at the wall heat transfer by conduction minus Kf into dt upon dy at y equal to 0 upon Ts minus T infinity. So are you able to relate these things with the fluid mechanics? Bolo. Here wall heat flux, there are momentum heat flux, wall momentum flux. But I told you just like this, through this formula of calculation of friction coefficient, that must be have a knowledge of velocity gradient, velocity profile must be known. Then only you know u is a function of y is given, you have differentiated and put y equal to 0 and find the friction coefficient at that point. Yes or no? Narottam. Similarly, if you want to find out heat transfer coefficient, and if, for example, if let's say same thing, this is the wall is there, okay sir, this is the vertical wall, and here the fluid is stagnant. Let's say fluid is flowing over it like this. Then again at the wall the heat transfer through conduction only, and in the rest of fluid the heat transfer by convection. The same phenomena is there, no problem. If Ts and here T infinity, let's say here air is flowing from here, it's T infinity, no problem sir. This is what Ts and this is T infinity. This is what the temperature distribution. Then here the heat transfer by Q conduction, and in the rest fluid by convection. So this is what the y. Now this is what x. At y equal to 0, minus kf dt upon dy at y equal to 0 is equal to h into Ts minus T infinity, and this h is equal to nothing minus kf into dt upon dy at y equal to 0 upon Ts minus T infinity. Any problem, beta? But this is local. Why local? Because dt upon dy is going to change from each location to location. Any problem, Mr. Astos? Now, if anyhow the temperature distribution is given to you, sir, my dear student, that's all about that, sir. They are the formula they have defined. Sir, क्या क्वेश्चन पूछते हो आप? तो लिखो ना, कौन मना कर रहा है? Then you should change the definition of heat transfer coefficient. Then we should change the definition of heat transfer coefficient. Sir, they are customs. Means the person who have defined this derivation, means they have given this equation in simplified form, h into a into Ts minus T infinity. They have given the simple form ki rate of heat transfer proportional to temperature difference. And because sir, in the convection problem, in the convection problem, we are not bothering about temperature distribution. Actually, we are more interested in the calculation of rate of heat transfer, because I told you already it's very difficult to calculate, it's very difficult to develop the temperature distribution. If now this you are seeing here very simple case, there are many complex where the heat transfer coefficient come into picture. I will discuss. And what is the importance of heat transfer coefficient? Now your question should be, sir, in this case, if we are calculating the rate of heat transfer through conduction, like Q conduction is equal to minus Kf into dt upon dy at y equal to 0, yes or no, then what is need of heat transfer coefficient? Already we are going to calculate the heat transfer by conduction, and same is through convection, same through convection na. So reason is that because we are not able to find the temperature distribution, because this involves this information, this is the local heat transfer, and this requires the knowledge of temperature distribution at each and every point along with the flow of plate. If I am going to take simple case, if the fluid is going to flow flat plate, then temperature gradient is going to change at each location. dt upon dy is not same through all. Well, temperature gradient, just like velocity gradient, is not same. Similarly, temperature gradient is also not same at each and every point on the wall. And can you imagine, if the fluid is going to flow flat plate, are you going to calculate the temperature distribution? How will you calculate temperature distribution? Is it very simple thing? To find the temperature distribution, you have to place, you can do for one case. For the experiment, you should place the at each and, let's say at 1 millimeter to at 4, 6, 8, at different millimeter you should place the thermocouples. You just add thermocouples. You have to just add thermocouples. One experiment you can do from your own, just place thermocouple at different distance in the wall. Fluid flowing, you found the thermocouple is measuring different temperature, and through that you can find the temperature profile, how the temperature is going to vary with y. But this is the thermocouple, this will give you only at this position. At this position what happened? Is it practically possible to find the temperature distribution at each and every location? Tell me please. That's why, to avoid that complexity, there is a method called as heat transfer coefficient method. The heat transfer coefficient is a method to find the rate of heat transfer in a complex conditions, in simplest as well as in the more complex condition where the profile is not well understood. Same thing, if you recall, I told you कि you can calculate the friction coefficient as tau w upon half rho u infinity square, that is what, mu into du upon dy at y equal to 0 upon half rho u infinity square. That I told you. But this requires the information about velocity gradient at each and every point on the wall. But I have an alternative approach. What? Friction coefficient is equal to 5.0 upon under root r ex. Here it does not require any information about the velocity gradient, it simply requires the knowledge of Reynolds number, rho u infinity x over mu, rho u infinity into x over mu. At any x you can find the Reynolds number and you can find the local friction coefficient. Yes sir? So similarly sir, this is the method of heat transfer coefficient that requires the knowledge of, if you want to calculate the heat transfer coefficient, that you must know through this method, you must know the temperature gradient at the wall at each and every location. Then you should go for average heat transfer coefficient. Okay, but it is not very easy task. Although when temperature distribution is given to you, then you can find the heat transfer coefficient through this method at that position, at that location on the plate. Clear? So the concept of heat transfer coefficient is important to find the rate of heat transfer in complex condition where the flow profile is not well understood, where you are not able to find the temperature distribution, because this method you can only use when temperature distribution is known to you. You can find the rate of heat transfer by this method when the temperature profile is known to you, but there are too many conditions are there where the flow is not well understood, because to find the temperature profile you must write the energy balance. Yes or no? Tell me please. Just try to think logically. What logic is? Logic says to find the temperature distribution, how the temperature profile, how the T is going to vary with the Y. Now, my dear student, you have to write the energy balance. Yes or no? Tell me please. You have to write energy balance. And tell me. And how can I write energy balance? I am going to give you a demonstration. What demonstration is there? I should assume a small differential element, just like I have assumed a small element in the boundary layer, dy, here dx, and over this we should apply the energy balance. And energy balance involve what? Listen, I told you in radial and in axial direction. In axial direction, let's say this is in axial direction, let's say I'm talking about heat transfer by two modes. Combined mode is there, because here temperature is, let's say, T at x, this is at T at x plus dx or delta x. Temperature different. And when I told you when the in this types of flow, when the fluid is going to flow with the velocity of mass by m dot, here also m dot, when the fluid is going to flow, there is a bulk flow is there. Whenever mass there is a bulk flow. Yes or no? When the bulk flow is taking place in presence of temperature difference or gradient, that causes the heat transfer. So in this case, in axial mode, the heat transfer is by combined mode. What combined mode? One is by random motion, other by bulk motion only. Yes or no? Tell me. One by random motion called as conduction, and other is by bulk motion, Q advection. Q advection, conduction and advection at x, at x. Here similarly Q conduction at x plus delta x, and here Q advection at x plus delta x. When I combine these two, this is combinedly I can say Q convection. Yes or no? At x. This combinedly is called as Q convection at x plus delta x. Clear, beta? This is what I talk about in axial direction. What about in y direction? Same thing here. But in basically, let's say I'm talking if the flow is one dimensional. One dimension means there is no flow is there. In this time, in this direction, there is no flow is there. Then only no bulk flow in this direction. Bulk flow is only in x direction. Am I right? If there is no bulk flow in this direction, then only the heat transfer in that direction is because of conduction. Yes or no? And obviously if you see the majorly flow is in this direction, then only advection flow is in this here. Here only Q conduction is there, Q conduction at y. Now Q conduction at y plus dy. Yes or no? So if you write the energy balance at steady state, let's say here 200 watt is energy transferred, here 180 watt is transferred through this. Where is the rest 20? The rest 20 watt of the heat transfer is going to transfer by the convective flow. By the convective flow, yes or no? It is combined mode. This is why energy cannot be created, cannot be destroyed. It can only transform from one form to other form. The energy must be balanced, na? So dear student, if you solve this equation, then you find the temperature distribution, and this you might got some information ki without in advection we must write m dot cp. What is q advection? M dot cp into t, and this mass rate involves the velocity. So can you say कि temperature distribution can't be solved by knowing the velocity distribution? You never supposed to solve the energy balance without solving the momentum equation, momentum balance. Because why it is so? Because the flow velocity, it's common sense. If we are going to change the velocity, let's say I am talking about energy balance, and if the flow is laminar and flow is turbulent, in both cases the rate of energy transfer is different, yes or no? It means the temperature distribution is strong function of velocity distribution. There is a high connection. Without having knowledge about the fluid mechanics, we are not supposed to understand or visualize the convective heat transfer, because temperature distribution is strongly function of velocity distribution. I told you, when the velocity gradient will change, then temperature gradient will also change. I told you now. These all things I will discuss when I will start the convection in detail. But here you should only understand. I told you already कि when the velocity gradient will change, then temperature gradient will also change. It means कहीं ना कहीं क्या है, temperature gradient is a function of velocity gradient, or temperature distribution is a function of velocity distribution. So before solving temperature distribution, we must have a velocity distribution. Yes or no? We must have a momentum equation. Clear? Without momentum balance, you are not supposed to solve the energy balance, because in the energy balance there is a advective flow involved, and advective flow involves the flow rate of velocity distribution. My dear student, you are never supposed to solve the temperature distribution without knowing the velocity distribution. It means we must know the energy balance as well as momentum balance. Energy balance as well as the momentum balance, both is required. And what happened, there are too many situations are there where the velocity profile is not well understood. For example, in turbulent flow, I told you, for example, if I am talking about mixing of liquid in a tank, if you are going to stirrer, here the profile is very complex. We only know the velocity distribution in the standard cases like laminar flow or turbulent flow in a pipe. What about the velocity profile in the packed bed? It's very complex, yes or no? Velocity profile in a packed bed is very complex. Velocity profile in the agitator is very complex. In those complex cases, as I told you, you are not supposed to find the temperature distribution, because once you find the temperature distribution, then you can find the rate of heat transfer by convection by knowing the dt upon dy at y equal to 0, by knowing the velocity gradient at the wall, because even the flow is very complex, but at the wall fluid is always stagnant and the heat transfer is going to initiate by conduction only at the wall. Because at the wall, in all scenarios, at the wall always the random molecular motion will dominate over the bulk motion. So if anyhow we are able to find temperature distribution, then what should I do? I should simply differentiate the temperature and make it y equal to 0, and we can multiply with the kf, and I can find the rate of heat transfer by conduction, and same is with convection. Yes or no? But the problem is that we must know temperature distribution, and to know the temperature distribution, we must know the velocity distribution. The velocity should be very clear. Our velocity profile should be very clear. Well established profile should be there. But there are too many scenarios are there where the velocity profile is not well understood. Very complex. So even the velocity profile is not well understood, then how can I write the energy balance? We will not in position to imagine the temperature distribution. Are you getting the point? In that case, we should only rely over what? The experimental results. And that's why the role of heat transfer coefficient come into picture. Is this clear? Why the heat transfer coefficient come into picture? They can ask you in the question, if you are saying at the wall the fluid is stagnant, then in all cases always the fluid is stagnant, then heat transfer at the wall is going to initiate by conduction, and same rate the heat transfer is going to transfer in the rest of the fluid by convection. Then what is the need of convective heat transfer coefficient if I know the temperature distribution at the wall? the question should be, your answer should be, sir, we can only find the temperature distribution if the profile is well understood by applying the momentum balance and by applying the energy balance. We can solve the two equations simultaneously to solve the temperature distribution, and by knowing the temperature distribution I can solve the rate of heat transfer at different locations, and then I can find the average heat transfer through the plate or through any object. But there are too many scenarios are there, sir, where it is very difficult to find the momentum distribution, or momentum where flow is not well understood, where the velocity profile is not well understood, flow is not well understood. In those complex cases, it's not possible to develop the energy balance or temperature distribution, and that's why we must have an alternative approach which can be used for the simplest as well as complex condition, and that's case is called as convective heat transfer in the fluid. Is this clear, beta? Because the all problem is only with the fluid motion, and the fluid motion problem of conduction is not in the solids. Problem of conduction is only in the fluid. We can't use the convective heat transfer in the whole fluid, because convection is only there when the fluid is in the motion, and that is only at the wall. Clear? कुछ क्लियर हुआ? Same thing in the mass transfer. There is a role of mass transfer coefficient. So mass transfer coefficient come into picture is just because of there are too many complex mass transfer applications are there where the flow is not well understood, and if the flow is not well understood, then we can't find the concentration profile. And once we can't find the concentration profile, then at the wall, although the mass transfer is by molecular diffusion only, still we are not find out the rate of mass transfer, because it's requires the knowledge of concentration profile. Because once the concentration distribution is known to, then only you should differentiate dc upon dy and y equal to 0, then we can find the rate of mass transfer. But we must know the concentration profile, and that we is not able to calculate at all conditions. Is this clear? That's why the role of mass transfer coefficient come into picture, which can be used for, which can be valid for complex as well as simplest problem of the mass transfer. Same thing, heat transfer coefficient, which is valid for simplest as well as complex cases of the heat transfer problems. So we can calculate the value of heat transfer coefficient for the simplest cases. I will show you through example how can I calculate the heat transfer coefficient for the simplest cases, and it's very simple. What should I do? To find the heat transfer coefficient expression, we must know temperature distribution, and to find the temperature distribution, what should I write? I should write the momentum balance and energy balance. I will each and everything I will show you through examples. Okay? So by writing the momentum balance and energy balance, I can find the temperature distribution. So again, momentum balance has to be compulsory. Without momentum balance, you can't solve the energy balance. Similarly, in the mass transfer, without momentum balance, you can't solve the component balance. Clear? That's why the role of fluid mechanics is important in the study of convective heat transfer. That's why every time I'm saying how much the importance of fluid flow or flow profile is in the convection heat transfer. Is this clear? Now the last mode is radiation. तो सोचो अभी तो ये इंट्रोडक्शन है, इतना डिटेल में बता दिया, तो व्हेन आई विल स्टार्ट द कन्वेक्शन देन व्हाट हैपन, है ना? तो यू शुड रिवाइज द फ्लूइड मैकेनिक्स at a regular level. Now it's radiation. Now basically I am talking about here thermal radiation. Why thermal radiation? Because any body above the absolute zero temperature will always emit the radiation. Even our body emits the radiation. Even your wall in which you are in the room wall in which you are sitting also emit the radiation. Even your laptop emits the radiation. So any body above the having finite temperature or above absolute zero temperature emits the radiation. But we are not talking about all types of radiation. We are only talking about those radiation which then fall on the body get heated, and which radiation when they get emit from the body get cooled. I'm talking about only those wavelength of the radiation, those spectrum of the radiation when they incident on the body get heated, and when they remove from the body get cooled. So that spectrum of the radiation is called as thermal radiation. So when thermal radiation fall on the body get heated, and when the thermal radiation get released from the body get cooled. So we are actually talking about thermal radiation. Okay, the thermal radiation is the energy emitted by matter that is at non-zero temperature. So in this chapter also we will discuss only about thermal radiation and also the radiation from the solid surface, although the radiation emission may also occur from the liquid and gases. So why the radiation will get emit? Because of change in electromagnetic configuration. By changes in the electron configuration or electromagnetic configuration of the constituents of the atom and molecules of substances, that causes the radiation. Clear? And that energy from the radiation, energy that emit from the radiation is in form of electromagnetic waves, that is called as photons or quantas. And that's why it does not require the medium. Even in the complete vacuum, that quanta can be easily transferred. So in the radiation, energy get transported in form of electromagnetic photons called as quantas. So radiation is the only mode of heat transfer that does not require any medium. Even in the absence of medium, the energy can be transferred, that is only radiation. While the rest two that we discussed, conduction and convection, that always require medium. The medium was fluid only in the case of convection, and medium was fluid and solid both in the case of conduction. Yes or no? And radiation heat transfer most efficient in the vacuum, because there is no any attenuation is there. Why efficient in the vacuum? Because there is no attenuation in the photons. बोलो क्लियर है या नहीं? And the rate of heat transfer by radiation is given by Stephen-Boltzmann law. According to Stephen-Boltzmann law, the rate of radiant energy, rate of thermal energy emission is proportional to 4th power of absolute temperature. So write some basic information about the radiation as well. Thermal radiation is energy emitted by matter. Matter may be solid, liquid or gas, that is at a non-zero temperature. The radiation is due to changes in electro electromagnetic configuration of the constituents atoms or molecules. Constituents atoms or molecules of substance or matter. The energy of the radiation is transported by electromagnetic waves called as quantas or photons. Okay, while the transfer of energy by conduction and convection requires the medium radiation does not. In fact, in absence of any medium, radiation transfer occurs more efficient. Most efficient in a vacuum only. क्लियर बेटा? क्या हुआ? ठीक है. Now consider radiation heat transfer process from surface. Let's say this is what surface is there. So there is a term is called emissive power. What is emissive power? The rate of energy radiant energy emitted per unit amount, or you can say rate of energy emitted per unit area, or you can say amount of radiant energy emitted per unit time per unit area of the surface. That is called as radiant energy. The radiation that is emitted from the surface originates from thermal energy of the matter. Thermal energy of matter, because this matter composed of some atoms and molecules, and that involves thermal energy. The thermal energy of the matter bounded by surface and the rate at which the energy is released per unit area and called as surface emissive power. So let's say this is the surface is there, and from the Stephen Boltzmann law, before this I would like to emissive power. What is emissive power? Amount of radiant energy emitted from surface through unit area per unit time, called as emissive power, called as total emissive power. So what is emissive power of any surface? So emissive power means, that is called E here. Emissive power means its unit is joule, amount of energy joule, per unit time per unit area, it means it's watt per meter square. Clear beta? So basically this is the radiant energy or rate of radiant energy emitted per unit surface through unit area unit time is called as emissive power. So this is what the surface is there under consideration, and the energy emitted from surface, this is what E, is given by the Stephen-Boltzmann law. According to Stephen-Boltzmann law, the total amount of energy that emitted, no sir, they are different. I am talking about emissive power, not emissivity. I will discuss later on what emissivity is there. So emissive power is nothing, it's simply the how much amount of energy get emitted through unit area unit time. It is clear? Through unit area unit time, how much amount of thermal energy get emitted from the body is called emissive power, and it's watt per meter square. Clear? The value of emissive power, the maximum, or you can say the upper limit of the emissive power is given by the Stephen-Boltzmann law. Upper limit means, let's say I have a two body and they are the same temperature. Let's say temperature T1 here. This is T. T is the surface temperature. At the same temperature, we have a 3 to 4 bodies are there. So all bodies will not able to emit the same amount of emissive power, although temperature is same. So that's why there should be an maximum power at the given temperature. So maximum power, maximum emissive power that can be produced by any surface is called as black body. Is this clear? So by Stephen-Boltzmann law, Stephen-Boltzmann law, this is a rate equation, Boltzmann law. Total emissive power of a black body is proportional to fourth power of absolute temperature. Capital T, and the constant is Stephen-Boltzmann constant. Stephen's-Boltzmann's constant. So here B for black body, proportional to fourth power of absolute, and EB is equal to constant is Stephen-Boltzmann constant. This is T power 4, where its unit is watt per meter square, and where sigma is Stephen-Boltzmann 5.67 into 10 power minus of 8 watt per meter square per Kelvin power 4. ठीक है बेटा, 5.67. So what is black body? Black body is the body which at a given temperature which can emit the maximum upper limit of emissive power. Is this clear? Because for example, let's say, try to stop writing. Let's say if you have two bodies are there, let's say one body here, two body here, three body here, and both are at temperature of 500 Kelvin. Then both body will emit the different value of emissive power. That's why there should be an idealized body which can produce the upper limit of emissive power, that is black body. So black body is the body which can emit the maximum emissive power at a given temperature. So it is a perfect emitter and as well as perfect absorber. Why perfect emitter or ideal emitter? Why? Because no body can emit the emissive power more than that body at a given temperature. Clear? So what is black body? Black body is an idealized and hypothetical body which can emit the maximum emissive power at a given temperature, or which can produce the upper limit of emissive power at a given temperature, and that is given by Stephen-Boltzmann law. It means if let's say if any body is there at temperature of 500 Kelvin, and if you want to find out emissive power, and if you put in this formula 5.67 and all and T is 500 Kelvin, then my dear student, this temperature is only absolute temperature, then that is the upper limit of emissive power. It's not a real surfaces. It's not emissive power of real surfaces. It's emissive power of black surfaces. Is this clear? All real surfaces emit the emissive power less than that, less than the upper limit. Is this clear? Let's say I'm taking a two persons are there. For example, in the class there are 145 students are there. All 145 students are accepting the same lecture from here, but all bodies, all persons are grasping different, and all will perform will different. All the performance of the every students will be different, है ना? That's why we should have an ideal condition, an ideal persons that can grasp maximum and then can produce the best. Similarly here, that there are number of bodies are there. If all bodies are the same temperature, then all bodies will emit the different amount of total radiant energy or total emissive power will be different. It means the rate of energy emitted from the surface will also depend upon the property of material. Yes or no? Because temperature is same, only the surface is going to change. So rate of radiant energy emitted from the surface will also depend upon the nature of surface as well as material of surface. Even the same material is there. But one time it is rough, other is smooth. Although it's made of same material, but once the surface is rough and one surface is smooth, in the both cases the radiant energy emitted from the surface at the same temperature is different. It means the energy emission or rate of energy emitted or emissive power of any surface is depend upon what? The nature of surface as well as temperature of surface. Along with the temperature and surface, also it depends upon the material of construction. Even the material of construction is same, but nature will be different, means rough and smooth, then still the rate of energy emission will be different. Is this clear, Mr. Praveen? So Stephen Boltzmann law has given the upper limit of energy that can be emitted from the surface at the given temperature. Nobody can emit the radiant energy more than this idealized body, black body, at the given temperature of T. किसी given temperature पर, at any given temperature. So if the two bodies are there, one is black body, other is real body, both at the same temperature, which body will emit the maximum emissive power? If let's say 5 bodies are there, and all 4 bodies are the real bodies and only one body is the black bodies, so which body, and all are the same temperature, which body will emit the maximum emissive power? Black body. And how can you calculate can you calculate the amount of maximum emissive power? Can you calculate if temperature is known to you? Can you calculate how? By the Stephen Boltzmann law, because Stephen Boltzmann law is only for black body, and this will provide the maximum or upper limit of emissive power. अभी देर है बेटा, रुक जाइए. So how can find the real? So it means for real surfaces, for real body, the term called is emissivity. Emissivity is simply the ratio of emissive power of the real surface to that of black surface, or non-black surface to the black surface. Is this clear? This is what emissivity, and that will take account of material and nature of surface. Mr. Praveen, now there is a emissivity is there. Emissivity is the ratio of emissive power of the non-black surface to the black surface. Total emissive power of non-black surface or real surface to that of black surface. It means if you want to find out the emissive power from the real surface at a given temperature, emissive power from the real surface, what should I do? I should multiply the emissive power of the black surface with the emissivity. Then, and for the black surface already we have sigma into T power 4. Yes or no? And T should be always absolute temperature. This is what the watt per meter square. This is what the emissive power of non-black surface when I multiply with emissivity. So what is the emissivity? Emissivity is the measure of Ability of material. Emissivity value is vary from 0 to 1. Yes or no? More than 0 and less than or equal to 1. 1 for black body. TS surface temperature. Clear beta? Sorry, equal to So what is the physical significance of emissivity? Emissivity is the radiative property of surface, and that is emissivity, and it provides a measure of how efficiently a surface emits the energy with respect to black body. है कि नहीं? It is a measure of how efficiently a surface emits energy related to what? Anyone? It is a measure of how efficiently, how effectively a surface emits the energy related to with respect to what? Anyone? Black body. It's a comparative study, and for all linear surfaces, for black surfaces or black body, emissivity is equal to 1. Clear beta? And for all linear surfaces, emissivity is less than 1. What is black body? Anyone? Black body is an idealized body which is act as a perfect emitter as well as perfect absorber. Why perfect emitter? Anyone? Why black body should be considered as a perfect emitter? Everyone knows that black body can emit the all amount of energy incident on it. But it's not only perfect absorber. Black body is the body which can absorb the all amount of radiant energy incident on it. Whatever energy will get incident, all amount of radiant energy incident on it will get absorbed. No fraction will transmit, no fraction will reflect, all will get absorbed. That's black body. Why it's perfect emitter? Because no body can emit the energy more than this at a given temperature. That's why it's perfect emitter. Clear? So black body, you can write black body is perfect emitter as well as perfect absorber. Why perfect absorber? Because it can absorb all amount of radiant energy incident on it of all wavelength. And why it's perfect emitter? Because no body can emit the energy more than this at a given temperature. It's the upper limit. It provides the upper limit of emissive power. Is this clear? Now my question is that is the black body is the only bodies which appears black in the color will act as a black body, or even the white any body whose color in the white can also act as a black body? बोलो भाई, आइए इधर आइए, कम हियर. ले वो प्लीज, आपका बुक कहाँ है? Question is that is all the bodies which are appear in black in color, if any body which appears black in color is the only body which act as a black body, or any body which may appear white in color can also be act as a black body? हाँ, बुक कहाँ है आपका? झंडा ऊंचा बोले हैं. अच्छा ठीक है, आप ना बुक ले गए आइए, उसमें W पढ़िए, M पढ़िए. हाँ चलिए पहले बताइए हमको ये क्या लिखा हुआ है। ये क्या लिखा हुआ है? ये न, ये क्या लिखा है? वॉच। तो डब्लू है ना ये तो। हाँ, डब्लू मतलब वॉच। अच्छा, ये क्या लिखा हुआ है? ये बताइए। ये अच्छा, ये बताइए दी पापा को, ये क्या लिखा है? वाह, ये क्या लिखा है? अरे वाह। हाँ, और ये क्या लिखा है बेटा? अच्छा, ये बताइए, ये बता दीजिए। दे रहा है। ये क्या लिखा है बता दीजिए तब, ये वाला। ये बताइए, ये क्या लिखा है? हम्म? पी। क्या लिखा है बताइए पहले। पी। भाई कोई बताएगा आंसर कि नहीं? Yes, any color body can be act as a black body. For example, snow. Snow is white in color, but it has ability to absorb nearly 90%, more than 90% of the incident radiation of given wavelength, of certain wavelength. Yes. Clear, beta? That's all for today. In the next lecture, we'll start the conduction in detail. That was only introduction chapter. The second chapter will start by conduction by tomorrow. ठीक है? Thank you so much.